So, in class, at the end of the lecture, we discussed the quadratic case of drag, where we had a Newton's second law, mdv/dt equals mg minus cv squared. So this was the problem where we had a baseball which was thrown downward. And in this case, we had only the quadratic term for our drag force. We went through the motions and we showed that the position of the baseball as a function of time is given by the terminal velocity squared divided by g times ln of the hyperbolic cosine of gt divided by v terminal, where we calculated v terminal to be the square root of mg divided c, and c is the quadratic drag coefficient. What I forgot to mention in class is that this expression here is true if we set y not to be 0. So initially it starts at 0 on the y-axis. That's where the ball is started when we dropped it downwards. So now, if we did this correctly, we should be able to show that in the limit as c approaches 0, we should recast our equation of motion for free fall without drag. The easiest way of doing this is by performing a Taylor series expansion about c equals 0 and then see what you get. So what we're going to do now is we're going to expand the following function as a Taylor series. So we're going to rewrite this above equation as f of x equals 1 over x ln of hyperbolic cosine of square root of x times t close parentheses, where now our x is nothing but the c. So hence we have to do a Taylor series expansion letting x go to 0. So as you might know already, if you do a Taylor series expansion and let's say we expanded about x equals a, in this case you know that you have to write f of x equals the function evaluated at a plus df over dx evaluated at a, so where x equals a, times x minus a, plus the second derivative of f respect to x, again evaluated at x equals a, times 1 over 2 factorial times x minus a squared. So you should have worked with this in the past and know that this is the Taylor series expansion. So in our case, if we expand this above expression here, so note that I really simplified this expression. I got rid of all the constants to be simplified. So just to show it that at the end we should get the form we are expecting. So we are again expanding this expression here about x equals 0. And if you do that, if you do the math, which I won't do right now, but you can go ahead and do it if you want to, you can show that f of x equals t over 2 minus t squared x over 12, and then you have other terms. So this really indeed looks like our free fall equation. So it does look like y of t equals y naught plus v naught t minus 1/2 a t squared. So this expression indeed reduces to something similar, because we have 1/2 times t, so this is probably the velocity term, and then we have this term, t squared x over 12, where x again is our c, so don't forget that. So again, this is the acceleration term times t squared right there. And then we do not have y naught is 0, because we did set it to 0. So y naught equals 0 in our case, as I told you earlier. So anyways, this is how you do this. So this is a complicated expression. It's not an easy expression to take the Taylor series expansion about x equals 0. But for a difficult expression like this, it is totally fine for you to use Wolfram alpha and do the expansion for a complicated expression. If it's a very simple one where it's easy to take the derivatives, go ahead and try this out. But in this case, it's okay if you use Wolfram alpha to give you the expansion. So now this concludes what I wasn't able to cover at the end of the class. And now please go over the next couple of videos, which will be about the main content in this module, where we're going to talk about oscillations, specifically simple harmonic oscillations.